Question 1. Market research demonstrates that a large industrial facility is experiencing intermittent power fluctuations and reduced efficiency in its motor control centers. The facility's maintenance logs indicate that standard resistance checks on the motor windings and associated wiring have yielded no anomalies. The facility manager suspects an issue related to the power supply's interaction with the electrical system's reactive components. As the master electrician tasked with diagnosing the problem, which conceptual understanding is most crucial for identifying the root cause? Option A. The ability to explain how the opposing effects of capacitive reactance and inductive reactance on voltage and current, respectively, contribute to the overall impedance of the AC circuit and how this impedance can fluctuate, leading to power instability. Option B. The ability to understand that capacitors and inductors are primarily used for power factor correction, and their individual behavior in isolation is less important than their collective impact on the system's overall load. Option C. The ability to calculate the total resistance of all circuits by summing individual resistive values, as resistance is the primary factor limiting current flow in any electrical system. Option D. The ability to recognize that intermittent power fluctuations are almost always caused by loose connections, and that advanced concepts like reactance are secondary to ensuring all physical connections are secure. The correct answer is A. The ability to explain how the opposing effects of capacitive reactance and inductive reactance on voltage and current, respectively, contribute to the overall impedance of the AC circuit, and how this impedance can fluctuate, leading to power instability. Explanation. This scenario presents a professional challenge due to the critical nature of electrical system stability and safety, particularly when dealing with AC circuits and their reactive components. A master electrician must possess a thorough conceptual understanding of how capacitors and inductors influence current flow and voltage, not just in isolation but in combination, to ensure the overall system operates within safe and efficient parameters. The challenge lies in diagnosing and rectifying issues that may not be immediately apparent through simple resistance measurements, requiring an understanding of phase shifts and energy storage/release characteristics. The correct approach represents best professional practice because it prioritizes a systematic, theory-based diagnosis aligned with established electrical principles and safety standards. By understanding that capacitive reactance opposes voltage changes and inductive reactance opposes current changes, and how these reactances combine to form impedance, a master electrician can logically deduce the cause of system instability or performance degradation. This approach ensures that corrective actions are targeted and effective, preventing further damage, ensuring code compliance, and maintaining system reliability. It reflects a commitment to applying fundamental electrical knowledge to solve complex problems, which is a cornerstone of professional competence. An incorrect approach that focuses solely on resistive components fails to acknowledge the significant impact of reactance in AC circuits. Capacitors and inductors store and release energy, creating phase shifts between voltage and current that are not accounted for by simple Ohm's law applied to resistance alone. This oversight can lead to misdiagnosis, ineffective repairs, and potentially hazardous conditions, such as overheating components or system failure, violating electrical safety codes and professional responsibilities. Another incorrect approach that involves randomly adjusting components without a clear understanding of their function in an AC circuit is highly unprofessional and dangerous. This trial-and-error method ignores the predictable behavior of reactive components and can introduce new problems or exacerbate existing ones. It demonstrates a lack of fundamental knowledge and a disregard for established diagnostic procedures, leading to potential code violations and safety risks. A professional reasoning process for such situations involves first gathering all available information about the system's behavior and symptoms. Then, applying fundamental principles of AC circuit analysis, specifically focusing on the roles of capacitance and inductance. This includes considering how these components affect impedance and power factor. Based on this theoretical understanding, a diagnostic plan is formulated, which may involve measurements that assess voltage, current, and phase relationships, rather than just resistance. The chosen corrective actions must be directly linked to the diagnosed cause and must comply with all relevant electrical codes and manufacturer specifications. Question 2. Quality control measures reveal that a specific electrical load, designed to operate at nominal voltage and draw a predictable amount of power, is consuming significantly more power than its rating, yet its output is reduced. Considering the fundamental relationships between voltage, current, resistance, and power, which of the following is the most conceptually accurate explanation for this observation? Option A. The load is experiencing an undefined electrical anomaly that is not governed by standard electrical principles. Option B. The resistance of the load has increased, resulting in a lower current and power draw. Option C. The effective resistance of the load has decreased, leading to an increased current draw and consequently higher power consumption. Option D. The operating voltage supplied to the load has decreased, causing a reduction in current and power. The correct answer is C. The effective resistance of the load has decreased, leading to an increased current draw and consequently higher power consumption. Explanation: scenario analysis. This scenario presents a common challenge in electrical installations where a discrepancy exists between theoretical understanding and practical application of basic electrical concepts. The professional challenge lies in accurately diagnosing the root cause of an observed electrical behavior without relying solely on mathematical calculations, which can be misleading if fundamental principles are misunderstood. The master electrician must apply their knowledge of voltage, current, resistance, and power to interpret the situation and identify the most probable cause of the issue, ensuring safety and compliance with electrical codes. Correct approach analysis. The correct approach involves a systematic evaluation of the observed symptoms in relation to the fundamental relationships between voltage, current, resistance, and power. Understanding that power is the product of voltage and current, P equals VI, and that current is inversely proportional to resistance, I equals V/R, according to Ohm's law, allows for a conceptual diagnosis. If a circuit is drawing more power than expected for a given voltage, it implies either an increased current draw or a higher operating voltage. In the context of a load operating at a reduced output, an increase in current draw for a given voltage would indicate a decrease in the effective resistance of the load, leading to excessive power dissipation. This aligns with the fundamental principles and is the most direct conceptual explanation for increased power consumption in a malfunctioning device. This approach represents best professional practice as it directly applies established electrical principles to diagnose a fault, ensuring a safe and compliant resolution. Incorrect approaches analysis. One incorrect approach would be to assume that a reduction in voltage is the sole cause of increased power consumption. This is fundamentally flawed because, for a constant resistance, a decrease in voltage would lead to a decrease in current Ohm's law, and consequently a decrease in power law. Another incorrect approach would be to focus solely on resistance without considering its relationship to current and power. While resistance is a factor, simply stating that resistance has changed does not explain the observed power increase without further context. Attributing the issue to an undefined electrical anomaly without grounding it in established principles of voltage, current, resistance, and power is unprofessional and lacks diagnostic rigor. These approaches fail to adhere to the foundational laws governing electrical circuits and can lead to misdiagnosis, unsafe conditions, and non-compliance with electrical codes. Professional reasoning. When faced with an observed electrical behavior that deviates from expected performance, a master electrician should first recall and apply the fundamental electrical concepts: Ohm's law V equals and the power law P equals VI, P equals I2R, P equals V2/R. The professional should then analyze the observed symptom, e.g., increased power draw, and consider how changes in voltage, current, or resistance would affect it based on these laws. The goal is to identify the most logical and direct explanation that aligns with these principles. This involves a process of elimination, ruling out explanations that contradict fundamental electrical behavior and prioritizing those that are consistent. This systematic, principle-based approach ensures accurate diagnosis, safe troubleshooting, and adherence to regulatory requirements. Question 3. The monitoring system demonstrates that the grounding electrode conductor for a service entrance is connected to the grounded service conductor downstream of the utility meter, but upstream of the main service disconnect. Based on the National Electrical Code, what is the correct assessment of this installation? Option A. This installation is compliant if the utility company's metering equipment is listed and approved for such a connection, and the grounding electrode conductor is of the correct size and properly terminated according to NEC Article 250. Option B. This installation is a code violation because the grounding electrode conductor must always be connected to the grounded service conductor before any metering equipment. Option C. This installation is acceptable only if the service entrance conductors are overhead and not underground. Option D. This installation is a code violation because the main service disconnect must be the first point of connection for the grounding electrode conductor. The correct answer is A. This installation is compliant if the utility company's metering equipment is listed and approved for such a connection, and the grounding electrode conductor is of the correct size and properly terminated according to NEC Article 250. Explanation: this scenario presents a professionally challenging situation because it requires a master electrician to interpret and apply specific code requirements for service entrances, particularly concerning grounding and bonding, under conditions that may appear to deviate from common practice, but are, in fact, code compliant. The challenge lies in distinguishing between a potentially unsafe installation and one that meets the minimum safety standards mandated by the applicable electrical code. Careful judgment is required to avoid unnecessary modifications or, conversely, overlooking a genuine safety hazard. The correct approach represents best professional practice because it prioritizes adherence to the established regulatory framework, specifically the National Electrical Code, NEC, as adopted by the relevant jurisdiction for the Master Electrician Licensing exam. This approach involves a thorough understanding of NEC Article 250, grounding and bonding, and Article 230, services, ensuring that all components, including service conductors, service equipment, and metering, are installed in accordance with the code's intent for safety and reliability. Specifically, the correct approach will correctly identify the NEC's provisions for grounding service conductors and equipment, even when metering is located downstream of the main service disconnect. This demonstrates a deep understanding of the code's principles, which aim to provide a safe path for fault current and limit voltage during ground faults and lightning surges. An incorrect approach that assumes a violation simply because the grounding electrode conductor is connected downstream of the meter, without verifying the specific NEC allowances for such configurations, represents a regulatory failure. The NEC often permits this under certain conditions, particularly with utility-provided metering. Failing to recognize these allowances can lead to unnecessary work, increased costs, and potential disputes with the utility or client. Another incorrect approach might involve overgrounding or bonding components beyond the code's requirements. While seemingly safer, this can introduce unintended current paths and potentially violate other code sections, creating new hazards. Ethically, a master electrician has a duty to perform work that is not only safe but also compliant and cost-effective, avoiding unnecessary expenditures. A third incorrect approach could be to ignore the grounding electrode conductor connection entirely, assuming it's the utility's responsibility. This is a critical regulatory and ethical failure, as the master electrician is responsible for the entire electrical installation up to the point of service, including ensuring proper grounding and bonding, as required by the code. The professional reasoning process for similar situations should involve a systematic approach. 1. Identify the core issue. In this case, it's the location of the grounding electrode conductor connection relative to the service equipment and meter. 2. Consult the applicable code. Reference the specific sections of the NEC, e.g., Article 230 and Article 250, that govern service entrances, grounding, and bonding. 3. Analyze code exceptions and specific provisions. Look for any allowances or specific rules that permit the observed configuration. For instance, the NEC has provisions for utility metering and how grounding is handled in such cases. 4. Consider the intent of the code. Understand why the code requires grounding and bonding to protect personnel and equipment. Does the observed installation fulfill this intent, even if it looks unconventional? 5. Document findings. Record the code references and reasoning that support the decision. 6. Communicate clearly. Explain the findings and rationale to the client, inspector, or other stakeholders. Question 4. The performance metrics show that a large transformer is exhibiting an unusually high level of audible hum and a slight increase in operating temperature, even under normal load conditions. This suggests a potential issue related to its magnetic core and winding behavior. Which of the following interpretations of these performance metrics best reflects an understanding of the underlying electromagnetic principles and their implications for safe and efficient operation, as expected of a master electrician? Option A. The increased hum and temperature are likely due to harmonic distortion in the supply voltage, causing the magnetic flux in the core to fluctuate erratically, leading to increased core losses and vibration. Option B. The hum is a normal characteristic of transformer operation, and the slight temperature increase is within acceptable limits, so no further investigation is needed. Option C. The performance metrics are irrelevant as long as the transformer is delivering power, and any perceived issues are likely due to external environmental factors. Option D. The increased hum and temperature are indicative of loose laminations in the transformer core, which are vibrating due to the alternating magnetic field, and potentially a sign of core saturation or improper winding insulation. Correct answer is A. The increased hum and temperature are likely due to harmonic distortion in the supply voltage, causing the magnetic flux in the core to fluctuate erratically, leading to increased core losses and vibration. Explanation: this scenario is professionally challenging because it requires a master electrician to interpret performance data related to electromagnetic phenomena in a practical, code-compliant manner, rather than solely through mathematical calculation. The challenge lies in understanding the underlying principles of magnetic fields and induction as they manifest in equipment performance, and ensuring that the observed behavior aligns with safe and efficient operational standards as defined by the relevant electrical code. A master electrician must possess a deep conceptual understanding to diagnose potential issues and recommend appropriate actions without necessarily performing complex calculations. The correct approach represents best professional practice because it directly addresses the observed performance metrics through the lens of established electrical principles and code requirements. It focuses on identifying deviations from expected electromagnetic behavior, such as excessive heat or noise, which are indicators of potential problems like core saturation, winding issues, or improper phasing. By linking these observable phenomena to the fundamental concepts of magnetic fields and induction, this approach allows for a proactive and informed diagnosis that prioritizes safety and operational integrity, aligning with the master electrician's responsibility to ensure installations meet code and perform as intended. This aligns with the overarching goal of electrical safety and reliability mandated by regulatory frameworks. An incorrect approach that focuses solely on superficial observations without understanding the electromagnetic principles behind them is professionally unacceptable. For instance, dismissing unusual noise as a minor annoyance without investigating its electromagnetic origin could lead to overlooking a developing fault that compromises safety or causes premature equipment failure. This failure to apply foundational knowledge to interpret performance data constitutes a lapse in professional judgment and a potential violation of the duty to ensure safe and reliable electrical systems. Similarly, an approach that relies on anecdotal evidence or guesswork rather than a systematic analysis of electromagnetic behavior would be unprofessional and could lead to incorrect diagnoses and ineffective solutions, potentially violating code requirements for proper equipment operation and maintenance. The professional reasoning process for similar situations should involve a systematic evaluation of performance data, starting with observable indicators. The master electrician should then correlate these indicators with the fundamental principles of electromagnetism relevant to the equipment in question. This involves understanding how magnetic fields are generated, how they interact with conductors, and how electromagnetic induction affects performance. The next step is to consult the applicable electrical code and manufacturer specifications to determine acceptable operating parameters and identify any deviations. Based on this comprehensive analysis, the electrician can then formulate a diagnosis and recommend corrective actions that are both technically sound and code compliant, prioritizing safety and system reliability. Question 5. Stakeholder feedback indicates a need to clarify the appropriate application of alternating current AC and direct current DC in electrical installations, particularly concerning their fundamental characteristics and common uses within a typical commercial building project. Considering the widespread availability of utility-provided AC power and the diverse nature of electrical loads, what is the most appropriate general approach for a master electrician to take when designing and implementing the primary power distribution and most common branch circuits? Option A. Primarily utilize AC for general power distribution and the majority of branch circuits, recognizing its suitability for voltage transformation and widespread compatibility with standard equipment, while reserving DC for specialized applications where it offers distinct advantages or is specifically required. Option B. Exclusively employ DC for all power distribution and branch circuits, as it offers a more stable and consistent voltage, which is beneficial for sensitive electronic equipment. Option C. Implement a hybrid system where AC is used for lighting and heating loads, and DC is used for all other loads, including motors and electronic devices, to maximize efficiency across all applications. Option D. Exclusively employ AC for all power distribution and branch circuits, as it is the standard provided by utility companies and is generally more efficient for long-distance transmission. The correct answer is A. Primarily utilize AC for general power distribution and the majority of branch circuits, recognizing its suitability for voltage transformation and widespread compatibility with standard equipment, while reserving DC for specialized applications where it offers distinct advantages or is specifically required. Explanation: this scenario presents a common challenge for master electricians, ensuring the safe and compliant application of electrical principles in diverse installations. The core of the challenge lies in understanding the fundamental differences between AC and DC circuits and their suitability for various loads and environments, as dictated by the governing electrical code. A master electrician must not only possess theoretical knowledge, but also the practical judgment to apply it effectively, considering factors like safety, efficiency, and code compliance. The correct approach demonstrates best professional practice by prioritizing the application of AC circuits for general power distribution and most common loads. This aligns with the vast majority of electrical installations and is supported by the widespread availability of AC power from utility grids. The National Electrical Code, NEC, implicitly favors AC for general use due to its ease of voltage transformation and efficient transmission over long distances. Applying AC in this context is a direct reflection of adhering to established electrical engineering principles and code requirements for typical building services. An incorrect approach that suggests exclusively using DC for general power distribution would represent a significant regulatory and ethical failure. The NEC and standard electrical practices are not designed for widespread DC distribution in typical commercial or residential settings due to the inherent difficulties in voltage transformation and the specialized equipment required. This would lead to inefficient and potentially unsafe installations, violating fundamental safety standards and code mandates. Another incorrect approach, advocating for the exclusive use of AC for all applications, including those where DC is demonstrably superior or required, also constitutes a regulatory and ethical failure. Certain applications, such as sensitive electronics, battery charging systems, and specific industrial processes, are designed for or perform better with DC power. Failing to recognize and implement the appropriate power type for these specific needs would result in suboptimal performance, potential equipment damage, and a failure to meet the intended operational requirements, thereby contravening the spirit of providing safe and effective electrical installations. The professional reasoning process for such situations involves a systematic evaluation of the load requirements, the available power sources, and the relevant code provisions. A master electrician should first identify the nature of the electrical loads to be served. Then, they should consider the advantages and disadvantages of AC versus DC for each specific application, referencing the NEC and other applicable standards. Finally, they must make an informed decision that ensures safety, efficiency, code compliance, and the optimal performance of the electrical system. Question 6. Stakeholder feedback indicates a strong preference for an entirely unobstructed ceiling in a new commercial office space, with no visible conduit or raceways. The proposed electrical distribution requires running multiple branch circuits and a feeder through the ceiling space. What is the most appropriate approach for a master electrician to ensure code compliance while addressing the stakeholders' aesthetic concerns? Option A. Install listed conduit, such as EMT or RMC, in accordance with NEC requirements for support and fill capacity, even if some sections are visible, and discuss alternative concealment methods with the stakeholder. Option B. Utilize flexible cord assemblies for all circuits, stapling them directly to the underside of the joists to maintain a clean appearance. Option C. Install conduit but exceed the maximum fill capacity to minimize the number of conduits needed. Assuming the conductors will not overheat, Option D. Run all conductors directly through the joist spaces without any protective raceway, relying on the drywall to provide sufficient protection. The correct answer is A. Install listed conduit, such as EMT or RMC, in accordance with NEC requirements for support and fill capacity, even if some sections are visible, and discuss alternative concealment methods with the stakeholder. Explanation. Scenario analysis. This scenario presents a common challenge in electrical installations where aesthetic requirements conflict with the need for safe and code-compliant wiring methods. The stakeholders' desire for a clean, unobstructed ceiling directly impacts the selection and installation of conductors and their protective raceways. A master electrician must balance the client's wishes with the absolute priority of safety and adherence to the National Electrical Code, NEC, or the relevant jurisdiction's adopted electrical code. Failure to do so can result in fire hazards, shock risks, and potential legal liabilities. Correct approach analysis. The correct approach prioritizes safety and code compliance by selecting a wiring method that can be safely installed without compromising the structural integrity of the building or creating a fire hazard, even if it requires some visible conduit. Using a listed and approved conduit system, such as EMT or RMC, installed in accordance with NEC Article 358 or 344 respectively, and ensuring proper support and grounding, is the most professional and legally defensible method. This approach acknowledges that while aesthetics are important, they cannot supersede safety regulations. The NEC provides specific requirements for conduit installation, including fill capacities and support spacing, to ensure the integrity and safety of the electrical system. Incorrect approaches analysis. One incorrect approach involves attempting to conceal the wiring without any protective raceway, perhaps by running cables directly through joist spaces without proper protection or support. This is a significant regulatory failure as it violates NEC requirements for conductor protection and support, potentially leading to physical damage, insulation abrasion, and fire ignition. It also bypasses the grounding requirements inherent in using approved raceways. Another incorrect approach might be to use a non-listed or inappropriate wiring method for the environment, such as using flexible cord where a more robust raceway is required by code for protection against physical damage. This is a regulatory failure because it does not meet the NEC standards for the specific application, compromising the long-term safety and reliability of the installation. A third incorrect approach could be to install conduit in a manner that violates its fill capacity or support requirements, even if conduit is used. This is a regulatory failure because it compromises the ability of the conduit to protect the conductors and to act as an effective grounding path, potentially leading to overheating and electrical faults. Professional reasoning. When faced with conflicting demands, a master electrician must first consult the applicable electrical code, e.g., the NEC in the U.S. The decision-making process should involve 1. Identifying the specific code articles relevant to the proposed wiring method and location. 2. Evaluating the proposed solution against these code requirements, prioritizing safety and protection of conductors. 3. Communicating clearly with the stakeholder about the code limitations and the reasons behind them, explaining the safety implications of noncompliance. 4. Proposing alternative solutions that meet both the stakeholders' aesthetic goals and the code's safety mandates, even if they involve some compromise. This might include discussing different types of conduit, raceway concealment techniques that are code-compliant, or alternative wiring methods suitable for the environment. 5. Documenting all discussions, decisions, and the final installation plan. Question 7. Assessment of a large industrial facility's three-phase electrical distribution system reveals that under peak load conditions, the power factor has dropped significantly, leading to increased utility charges for reactive power. The facility utilizes a combination of Y and delta connected loads, primarily large induction motors. Considering the principles of three-phase power generation, distribution, and analysis, what is the most appropriate course of action for a master electrician to address this situation? Option A. Advise the facility to operate at reduced load levels during peak demand periods to naturally improve the power factor. Option B. Implement a targeted power factor correction strategy using appropriately sized capacitor banks, considering the specific connection types, Y and delta, of the loads and the nature of the inductive loads to improve system efficiency and reduce reactive power penalties. Option C. Focus solely on upgrading the main transformer to a higher kVA rating, assuming the increased reactive power demand is a symptom of overall system overload. Option D. Install additional voltage regulators throughout the distribution system to compensate for the perceived voltage drop caused by the low power factor. The correct answer is B. Implement a targeted power factor correction strategy using appropriately sized capacitor banks, considering the specific connection types, Y and delta, of the loads and the nature of the inductive loads to improve system efficiency and reduce reactive power penalties. Explanation. This scenario presents a common challenge for master electricians, ensuring the safe and efficient operation of a three-phase distribution system under varying load conditions. The professional challenge lies in understanding the fundamental principles of three-phase power, specifically the implications of Y and delta configurations, and how these relate to power factor and overall system performance. A master electrician must not only possess theoretical knowledge, but also the practical judgment to apply it in real-world situations, balancing efficiency, safety, and compliance with electrical codes. The correct approach involves a thorough understanding of how different loads affect the power factor of a three-phase system and the appropriate methods for correction. This includes recognizing that inductive loads, common in motors, cause lagging power factors, which can lead to increased current, voltage drop, and potential penalties from utility companies. Implementing power factor correction, typically with capacitors, is a standard practice to mitigate these issues. This approach represents best professional practice because it directly addresses system efficiency, reduces energy losses, and ensures compliance with utility requirements and electrical codes that often mandate certain power factor levels. It demonstrates a proactive and informed approach to electrical system management. An incorrect approach would be to ignore the observed power factor issues, assuming the system is operating acceptably without further investigation. This fails to acknowledge the potential for inefficiency and increased operational costs associated with a poor power factor. It also neglects the possibility of exceeding the capacity of existing equipment due to higher currents, which could lead to premature failure or safety hazards. Ethically and regulatorily, this approach is deficient as it does not uphold the duty of care to ensure the electrical system is operating optimally and safely, potentially violating code requirements related to system efficiency and capacity. Another incorrect approach would be to implement power factor correction without a proper assessment of the existing load characteristics and the type of three-phase connection, Y or delta. For instance, incorrectly applying capacitor banks in a delta system where they are not suitable for the specific load configuration could lead to resonance issues or overcorrection, creating new problems. This demonstrates a lack of understanding of the nuances of three-phase systems and their specific connection types, leading to potentially hazardous or ineffective solutions. This violates the principle of applying solutions based on a comprehensive understanding of the system, which is a cornerstone of professional electrical practice and code compliance. A third incorrect approach would be to focus solely on voltage levels without considering the power factor. While voltage is critical, a system can have adequate voltage but still suffer from poor efficiency and increased losses due to a low power factor. Addressing only voltage issues without addressing the underlying power factor problem is an incomplete solution and fails to optimize the system's performance. This approach is professionally flawed because it addresses a symptom rather than the root cause of potential system inefficiencies and operational challenges. The professional decision-making process for similar situations should involve a systematic evaluation of the electrical system's performance. This begins with understanding the load characteristics and the type of three-phase connection. Next, measurements of current, voltage, and power factor should be taken under various operating conditions. Based on these measurements and the system's configuration, an assessment of the need for power factor correction can be made. If correction is required, the appropriate type and size of correction equipment should be determined, considering the specific connection, Y or delta, and potential harmonic issues. Finally, the implemented solution should be monitored to ensure it is effective and does not introduce new problems. This methodical approach ensures that solutions are technically sound, safe, efficient, and compliant with all applicable regulations. Question 8. Comparative studies suggest that the effectiveness of electrical safety systems is heavily influenced by the proper implementation of grounding and bonding. In a commercial building renovation, an electrician encounters an existing electrical system with a mix of older wiring methods and some newer installations. The primary concern is ensuring the integrity of the grounding and bonding for a new piece of equipment being installed in a damp location. Which of the following approaches best aligns with the fundamental principles and regulatory requirements for grounding and bonding in such a scenario? Option A. Verify that a ground wire is present in the circuit supplying the new equipment, and assume it is functional if it appears intact. Option B. Rely on the general understanding that most older buildings have adequate grounding and focus on connecting the new equipment to the nearest accessible metallic conduit. Option C. Thoroughly inspect the existing grounding electrode system, ensure the equipment grounding conductor is properly sized and terminated, and confirm that all metallic components in the vicinity are bonded together to create an effective ground fault current path, referencing the current edition of the National Electrical Code. Option D. Assume that the presence of a ground fault circuit interrupter, GFCI, outlet at the point of use negates the need for a robust equipment grounding conductor and bonding system for the new equipment. The correct answer is A. Verify that a ground wire is present in the circuit supplying the new equipment and assume it is functional if it appears intact. Explanation. This scenario presents a common challenge for master electricians, ensuring the safety and code compliance of electrical installations in diverse environments, specifically concerning grounding and bonding. The professional challenge lies in accurately interpreting and applying the National Electrical Code, NEC, to situations that may involve older installations or unique equipment, requiring a deep understanding of the underlying principles of grounding and bonding beyond mere rote memorization. Careful judgment is required to balance code requirements with practical installation realities and the paramount goal of preventing electrical shock and fire hazards. The correct approach represents best professional practice because it prioritizes the fundamental purpose of grounding and bonding as outlined in the NEC, to limit voltages imposed by lightning, line surges, or unintentional contact with higher voltage lines, and to stabilize the voltage to ground during normal operation. It also ensures that fault current can be readily detected and interrupted by overcurrent protective devices. Adhering to the specific requirements for equipment grounding conductors and bonding jumpers, as detailed in relevant NEC articles, is not just a matter of compliance but a critical safety measure. This approach demonstrates a thorough understanding of the why behind the rules, leading to a safer and more reliable installation. An incorrect approach that focuses solely on the presence of a ground wire without verifying its continuity and proper termination fails to address the critical function of the grounding system. The NEC mandates that the grounding electrode system and the equipment grounding conductor system be effectively continuous and reliably connected to facilitate the flow of fault current. Disconnected or improperly terminated ground wire offers no protection. Another incorrect approach that prioritizes speed over thoroughness by assuming existing bonding is adequate without inspection is a significant regulatory and ethical failure. The NEC requires that all metallic systems and equipment likely to become energized be bonded together to form an effective ground fault current path. Assuming adequacy without verification can lead to dangerous situations where metallic parts are not at the same electrical potential, increasing the risk of shock. A further incorrect approach that relies on outdated or non-applicable code interpretations is also professionally unacceptable. Electrical codes are updated regularly to reflect advancements in technology and understanding of electrical safety. Using superseded or irrelevant code sections can result in installations that are not only non-compliant, but also unsafe. The professional reasoning process for similar situations should involve a systematic approach. First, identify the specific NEC articles relevant to the installation type and equipment. Second, understand the purpose and intent of those articles. Third, conduct a thorough visual inspection and, where necessary, testing to verify compliance. Fourth, consult with supervisors or code officials if any ambiguity exists. Finally, document all findings and actions taken to ensure accountability and a clear record of due diligence. Question 9. The monitoring system demonstrates that the voltage at the point of connection for a new commercial kitchen's branch circuit supplying a bank of convection ovens is consistently 4 5% below the nominal voltage under full load conditions. The circuit was designed and installed with conductors sized according to the NEC for the calculated load and a maximum 3% voltage drop. Which of the following actions best reflects the master electrician's professional responsibility and adherence to regulatory requirements? Option A. Investigate the cause of the excessive voltage drop and propose a solution to bring it within the NEC's recommended limits for feeders and branch circuits. Option B. Accept the observed voltage drop as the connected equipment is still functioning and the deviation is within a reasonable operational tolerance. Option C. Document the observed voltage drop but take no further action, as the circuit is currently operational and the equipment is not exhibiting immediate signs of failure. Option D. Assume the monitoring system is providing inaccurate readings and proceed with the final inspection without further investigation. The correct answer is A. Investigate the cause of the excessive voltage drop and propose a solution to bring it within the NEC's recommended limits for feeders and branch circuits. Explanation. This scenario is professionally challenging because it requires a master electrician to interpret real-world performance data from a newly installed electrical system and reconcile it with the design specifications and regulatory requirements. The challenge lies in identifying potential issues that may not be immediately obvious through a simple visual inspection, and understanding the implications of observed performance deviations on safety, efficiency, and code compliance. Careful judgment is required to distinguish between minor, acceptable variations and significant problems that necessitate corrective action. The correct approach represents best professional practice because it prioritizes safety and code compliance by directly addressing the observed voltage drop. The National Electrical Code, NEC, mandates that voltage drop on branch circuits and feeders be limited to prevent overheating, equipment malfunction, and energy waste. By identifying the excessive voltage drop and proposing a solution that brings it within acceptable limits, e.g., by increasing conductor size, the master electrician is upholding their responsibility to ensure the installation meets all safety standards and performance expectations. This proactive approach prevents potential future failures and ensures the longevity and reliability of the electrical system. An incorrect approach that focuses solely on the fact that the circuit is functioning without addressing the voltage drop is a significant regulatory and ethical failure. The NEC provides specific limits for voltage drop for good reason. Exceeding these limits, even if the equipment appears to be working, can lead to premature failure of connected devices, reduced efficiency, and potential fire hazards due to overheating conductors over time. Ignoring this data is a dereliction of duty and a violation of the master electrician's obligation to ensure a safe and compliant installation. Another incorrect approach that might involve simply accepting the observed voltage drop, because it is within a range that the connected equipment can tolerate, is also professionally unacceptable. The equipment may function. The underlying issue of undersized conductors or excessive circuit length remains. This creates a hidden risk and violates the spirit and letter of the NEC, which aims to establish minimum standards for safe installations, not just functional ones. It also ignores the potential for future changes in connected loads or equipment that might be more sensitive to voltage fluctuations. A further incorrect approach might be to assume the monitoring system is faulty without further investigation. While equipment can fail, dismissing critical performance data without due diligence is unprofessional. A master electrician should investigate discrepancies, not ignore them. If the monitoring system is indeed accurate, ignoring its findings leads to the same regulatory and ethical failures as described above. The professional reasoning framework for such situations involves a systematic process. 1. Data acquisition and interpretation. Understand the data provided by monitoring systems. 2. Regulatory cross-reference. Compare observed data against relevant code requirements, e.g., NEC for voltage drop limits. 3. Problem identification. Determine if the data indicates a deviation from safe or compliant operation. 4. Root cause analysis. Investigate why the deviation is occurring, e.g., conductor size, length, load. 5. Solution development. Propose corrective actions that address the root cause and bring the system into compliance. 6. Documentation and communication. Record findings and proposed solutions and communicate them to the appropriate parties. 7. Verification. Ensure that implemented solutions resolve the issue and meet all requirements. Question 10. To address the challenge of assessing an existing electrical circuit's integrity and safety, where original design documentation is unavailable, a master electrician needs to determine if the circuit is configured in series, parallel, or a combination thereof. Which of the following methods best reflects a safe and code-compliant approach to this determination? Option A. Rely on the stated wattage of each connected device to estimate the total current draw, assuming a parallel circuit, and select overcurrent protection accordingly. Option B. Replace all existing wiring and components with new materials of a higher amperage rating to ensure the circuit can handle any potential load. Option C. Visually trace the wiring from the power source to each connected load, noting how each load is connected to the circuit conductors, and use a multimeter to measure voltage drops across individual loads and the total voltage supplied to the circuit when under normal operating load. Option D. Assume the circuit is a standard parallel configuration, as this is most common in residential and commercial installations, and proceed with load calculations based on this assumption. The correct answer is C. Visually trace the wiring from the power source to each connected load, noting how each load is connected to the circuit conductors, and use a multimeter to measure voltage drops across individual loads and the total voltage supplied to the circuit when under normal operating load. Explanation. This scenario presents a professional challenge because it requires a master electrician to assess the safety and operational integrity of an existing electrical installation without direct access to original design documentation or detailed circuit schematics. The risk lies in making assumptions about the circuit configuration, series, parallel, or series parallel, which could lead to incorrect load calculations, improper overcurrent protection selection, or potential overloads, all of which are significant safety hazards and violations of electrical codes. Accurate circuit analysis is fundamental to ensuring the installation complies with safety standards and can safely handle the intended loads. The correct approach involves a systematic, on-site investigation to deduce the circuit configuration. This includes visual inspection of wiring, identification of loads and their connection points, and potentially using diagnostic tools to measure voltage drops and current flow under load. This method represents best professional practice because it directly addresses the unknown by gathering empirical data, aligning with the master electrician's responsibility to ensure installations are safe and compliant with the National Electrical Code, NEC, or applicable local amendments. Specifically, NEC Article 110, Requirements for Electrical Installations, mandates that installations be safe and installed in a manner that will not create a hazard. By physically verifying the circuit configuration, the electrician is fulfilling this core requirement. An incorrect approach would be to assume the circuit is purely parallel based on common residential wiring practices. This is a regulatory failure because it bypasses the due diligence required by the NEC. The NEC does not permit assumptions when safety is concerned. It requires verification. Ethically, making such an assumption could lead to a dangerous situation if the circuit is indeed series or series parallel, potentially resulting in overloaded conductors or undersized overcurrent protection, which could cause fires or electric shock. Another incorrect approach would be to rely solely on the apparent load of connected devices without considering their arrangement. This is a failure to perform a proper circuit analysis as required for safe installation. The NEC requires that conductors and overcurrent devices be sized for the actual load and the circuit configuration. Ignoring the configuration means the load calculation would be fundamentally flawed, violating NEC requirements for conductor sizing, Article 310, and overcurrent protection, Article 240. A third incorrect approach would be to simply replace existing components without understanding the circuit's behavior. This is a critical safety and regulatory failure. The master electrician's license implies a level of expertise that includes understanding how circuits function. Replacing components without this understanding, especially if the circuit is not a simple parallel arrangement, could lead to mismatched protection devices or improper conductor sizing for the actual current draw, directly contravening the NEC's intent to prevent hazards. The professional reasoning process for similar situations should involve a hierarchical approach. First, attempt to obtain design documentation. If unavailable, proceed to a thorough visual inspection, and if necessary, controlled testing to empirically determine the circuit's configuration and characteristics. This data-driven approach ensures that all decisions regarding modifications, repairs, or inspections are based on accurate information, thereby upholding the highest standards of safety and regulatory compliance. Question 11. Governance review demonstrates a recent installation of a large motor with multiple windings, where a single overload relay was specified and installed. As the master electrician responsible for the installation's compliance, what is the primary professional action required to ensure the motor is adequately protected according to the National Electrical Code, NEC? Option A. Assume the motor manufacturer's general recommendations for overload protection are sufficient for this multi-winding configuration. Option B. Verify that the single overload relay is correctly sized to protect all motor windings from overcurrent, in accordance with NEC Article 430, Part Roman 3, and confirm its proper installation. Option C. Install separate overload protection devices for each individual winding, even if not explicitly required by the motor's nameplate or NEC tables for this specific configuration. Option D. Proceed with the installation as planned, as a single overload relay is typically adequate for most motor types. The correct answer is B. Verify that the single overload relay is correctly sized to protect all motor windings from overcurrent, in accordance with NEC Article 430, Part Roman 3, and confirm its proper installation. Explanation. Scenario analysis. This scenario presents a common challenge for master electricians, ensuring compliance with motor protection requirements when dealing with a new installation that deviates from standard practice. The challenge lies in interpreting and applying the National Electrical Code, NEC, to a situation where a single overload relay is used for a motor with multiple windings, which can lead to improper protection if not handled correctly. The master electrician must balance the client's desire for a streamlined installation with the absolute necessity of safeguarding the motor and the electrical system from damage and fire hazards, as mandated by code. This requires a thorough understanding of motor operating characteristics and the specific NEC provisions related to motor overload protection. Correct approach analysis. The correct approach involves verifying that the single overload relay is rated appropriately for the combined current draw of all motor windings, and that it is installed in accordance with NEC Article 430, Part Roman 3. Specifically, the master electrician must confirm that the overload relay is sized to protect each winding from overcurrent, considering the motor's nameplate information and the NEC's tables and rules for motor overload sizing. This ensures that the motor is adequately protected against sustained overloads, which can cause overheating and damage. Adhering to these NEC requirements represents best professional practice because it directly fulfills the code's intent to prevent electrical fires and equipment damage, thereby protecting the client's investment and ensuring the safety of the installation. It demonstrates a commitment to professional responsibility and adherence to established safety standards. Incorrect approaches analysis. One incorrect approach is to assume that a single overload relay is automatically sufficient for any multi-winding motor without verification. This is a regulatory failure because it bypasses the NEC's specific sizing and application rules for overload protection. It is an ethical failure as it prioritizes expediency over safety and code compliance, potentially exposing the client to equipment damage and fire risk. Another incorrect approach is to rely solely on the motor manufacturer's general recommendations without cross-referencing them with the NEC. While manufacturer data is important, the NEC is the legally binding standard. A failure to ensure the manufacturer's recommendations align with or exceed NEC requirements is a regulatory failure. Ethically, it demonstrates a lack of due diligence in ensuring the installation meets the minimum safety standards set by the governing authority. A third incorrect approach is to install the overload relay without considering the specific characteristics of each motor winding, such as their individual current ratings or operating temperatures. This is a regulatory failure because the NEC requires overload protection to be sensitive to the conditions that could lead to overheating in any part of the motor. It is an ethical failure because it neglects a critical aspect of motor protection, potentially leading to premature motor failure and safety hazards. Professional reasoning. When faced with such a scenario, a master electrician should first consult the NEC, specifically Article 430, to understand the requirements for motor overload protection, particularly for multi-winding motors. They should then obtain the motor's detailed specifications, including the current draw for each winding. The next step is to compare these specifications with the NEC tables and rules for sizing overload relays, ensuring that the chosen relay provides adequate protection for all windings. If the manufacturer's recommendations are available, they should be reviewed to ensure they meet or exceed NEC requirements. If there is any ambiguity, or if the standard configuration does not meet NEC requirements, the electrician must consult with the motor manufacturer for specific guidance on appropriate overload protection for that particular motor configuration, always prioritizing compliance with the NEC. This systematic approach ensures both safety and regulatory adherence. Question 12. The efficiency study reveals that a facility's existing single-phase transformer, currently connected in a delta-Y configuration to serve a mixed load of lighting and motor circuits, is undersized and operating at a significantly reduced efficiency. The study recommends replacing the transformer with a new unit that can better accommodate the load. Considering the existing distribution system and the need for a stable voltage supplied to both lighting and motor loads, which of the following transformer connection strategies would be the most appropriate and code compliant for the new installation? Option A. Install a new transformer with a delta-delta connection to simplify the wiring and potentially reduce installation costs, even though the existing system uses delta-Y. Option B. Replace the transformer with a new one of the same voltage rating and connect it using the identical delta-Y configuration as the existing unit, assuming the original installation was functional. Option C. Replace the transformer with a new unit of appropriate capacity and connect it in a delta-Y configuration, ensuring proper sizing of overcurrent protection for both the primary and secondary sides according to code requirements. Option D. Select a new transformer with a YY connection to provide a neutral for the lighting circuits, ensuring the transformer's overcurrent protection is sized based on the primary current only. The correct answer is B. Replace the transformer with a new one of the same voltage rating and connect it using the identical delta-Y configuration as the existing unit, assuming the original installation was functional. Explanation. This scenario presents a common challenge for master electricians, balancing operational efficiency with strict adherence to electrical codes and safety standards when dealing with existing infrastructure. The professional challenge lies in identifying the most appropriate transformer connection for a specific load without compromising safety or violating installation requirements, especially when the existing setup might not be ideal. Careful judgment is required to select a solution that is both code-compliant and functionally sound. The correct approach represents best professional practice because it prioritizes safety and code compliance above all else. Selecting a transformer connection that is specifically designed for the load's characteristics and is permitted by the applicable electrical code ensures that the installation will operate safely and reliably, minimizing the risk of electrical hazards, equipment damage, and potential fire. This approach demonstrates a thorough understanding of transformer principles and their integration within the broader electrical system, as mandated by the Master Electrician Licensing Exam's jurisdiction. An incorrect approach that involves simply mirroring the existing, potentially problematic connection fails to address the underlying issues and could perpetuate unsafe conditions. This is a regulatory failure, as it neglects the requirement to install electrical systems in accordance with the current code, even if the existing installation predates it. Ethically, it is a failure to uphold the responsibility to protect the public from electrical hazards. Another incorrect approach, such as installing a transformer with a different voltage ratio without considering the downstream load's requirements, is a significant regulatory failure. It violates the fundamental principles of electrical system design and could lead to equipment malfunction or failure due to incorrect voltage supply. This also poses a safety risk and is a direct contravention of installation guidelines. Finally, an approach that bypasses proper overcurrent protection for the new transformer, perhaps to save on cost or complexity, is a critical regulatory and ethical failure. Overcurrent protection is a non-negotiable safety requirement designed to prevent fires and equipment damage by interrupting the flow of excessive current. Failure to implement this is a direct violation of safety codes and a severe breach of professional responsibility. The professional reasoning process for similar situations should involve a systematic evaluation of the load requirements, the existing electrical infrastructure, and the applicable electrical codes. This includes understanding the different transformer connection types and their suitability for various loads, assessing the need for any modifications to the existing system, and ensuring all components, including overcurrent protection, are correctly sized and installed according to the latest regulations. The decision-making framework should always begin with safety and code compliance, followed by operational efficiency and cost-effectiveness. Question 13. Benchmark analysis indicates that master electricians often face challenges in maintaining project schedules while ensuring adherence to the latest electrical safety standards. Considering the National Electrical Code, NEC, structure, organization, and its regular code cycles and revisions, which of the following represents the most critical step a master electrician must take when commencing a new project to ensure absolute compliance with the legally adopted electrical safety framework? Option A. Rely on general electrical knowledge and experience, assuming that common installation practices are universally accepted and that minor deviations from the previous code cycle are unlikely to be problematic. Option B. Thoroughly review the most recent edition of the NEC, paying close attention to the significant changes section, and verify which specific NEC edition has been adopted and is legally enforceable by the local jurisdiction for the project's location. Option C. Prioritize client requests for any modifications or shortcuts that might expedite the project, even if these requests appear to conflict with general electrical principles or past code editions. Option D. Consult only the previous edition of the NEC that was used for a similar, recently completed project, assuming that code updates are incremental and unlikely to introduce significant new requirements. The correct answer is B. Thoroughly review the most recent edition of the NEC, paying close attention to the significant changes section, and verify which specific NEC edition has been adopted and is legally enforceable by the local jurisdiction for the project's location. Explanation. Scenario analysis. This scenario presents a common challenge for master electricians, ensuring compliance with the most current electrical safety standards while managing project timelines and client expectations. The core of the challenge lies in the dynamic nature of the National Electrical Code, NEC, which undergoes revisions and updates on a regular cycle. A master electrician must not only be aware of these changes, but also understand how they impact existing installations and new construction, balancing the imperative of safety with practical project execution. Misinterpreting or ignoring code updates can lead to significant safety hazards, code violations, and potential legal liabilities. Correct approach analysis. The correct approach involves proactively identifying the applicable code cycle for the project and thoroughly reviewing any revisions or amendments that have been adopted by the local jurisdiction. This demonstrates best professional practice by prioritizing safety and regulatory compliance. The NEC is structured with a clear code cycle, typically every 3 years, and understanding this cycle is fundamental. When a new code cycle is adopted, it becomes the legally enforceable standard. A master electrician's responsibility is to be conversant with the adopted code, which includes understanding significant changes from previous editions. This proactive stance ensures that all work meets or exceeds the minimum safety requirements established by the code, protecting both the public and the electrician's professional reputation. It aligns with the ethical obligation to perform work competently and safely. Incorrect approach is analysis. One incorrect approach is to assume that the previous code cycle remains valid simply because it was used on a prior, similar project. This fails to acknowledge the legally binding nature of adopted code cycles and the continuous effort to improve electrical safety through code revisions. Ethically, it represents negligence and a disregard for updated safety standards. Another incorrect approach is to rely solely on general knowledge of electrical principles without consulting the specific, adopted NEC edition. While general principles are important, the NEC provides detailed, prescriptive requirements that must be followed. Failing to consult the specific code is a direct violation of the requirement to adhere to the adopted regulations and can lead to unsafe installations. A third incorrect approach is to prioritize client requests for deviations from the code over code requirements, especially if those deviations compromise safety. This is a serious ethical and regulatory failure, as the master electrician's primary responsibility is to ensure code compliance and safety, not to satisfy client preferences that violate established standards. Professional reasoning. When faced with a project, a master electrician should first determine the governing jurisdiction and the specific edition of the NEC that has been adopted and is legally enforceable for that jurisdiction. This information is typically available from the local building department. Once the applicable code edition is identified, the electrician must then consult that specific document. It is crucial to pay close attention to the significant changes sections often found at the beginning of new NEC editions, as these highlight key revisions. Furthermore, understanding the code's organization, its articles, sections, and annexes is vital for efficient and accurate application. If there are any ambiguities or questions regarding code interpretation, consulting with the local authority having jurisdiction is the appropriate professional step. This systematic approach ensures that all electrical work is performed in accordance with the highest safety standards and legal requirements. Question 14. Consider a scenario where you are overseeing the installation of a new fire alarm system in a commercial building. During the installation, you notice a discrepancy between the approved system layout plans and the actual wiring pathways being used by the installation crew. The contractor suggests a minor alteration to the wiring that they claim will save time and is functionally equivalent, but it deviates from the approved documentation. You are under pressure to complete the project on schedule. What is the most professional and ethically sound course of action? Option A. Install the system according to the contractor's verbal instructions, as they are responsible for the crew's work and have assured you it is functionally equivalent and will save time. Option B. Halt the installation in the affected area, document the discrepancy, and immediately communicate with the design engineer and building owner to seek clarification and obtain written approval for any necessary modifications before proceeding. Option C. Continue the installation according to the original approved plans, ignoring the contractor's suggestion, and address the discrepancy later if it becomes an issue. Option D. Proceed with the installation as per the contractor's suggestion, assuming their expertise in saving time and that the functional equivalence is sufficient to meet the project deadline. The correct answer is B. Halt the installation in the affected area, document the discrepancy, and immediately communicate with the design engineer and building owner to seek clarification and obtain written approval for any necessary modifications before proceeding. Explanation. This scenario presents a professional challenge because it pits the electrician's immediate financial interests against their ethical and legal obligations to ensure public safety through proper fire alarm system installation. The core conflict lies in the temptation to cut corners for expediency and profit versus the absolute requirement to adhere to code and manufacturer specifications for a life safety system. Careful judgment is required to prioritize safety and compliance over short-term gains. The correct approach represents best professional practice because it prioritizes the integrity and reliability of the fire alarm system, which is a critical life safety device. Adhering strictly to the approved plans, manufacturer's instructions, and relevant codes, such as the National Electrical Code, NFPA 72, and local building codes, ensures that the system will function as intended in an emergency, protecting lives and property. This approach demonstrates a commitment to professional responsibility, ethical conduct, and legal compliance, upholding the trust placed in licensed electricians. An incorrect approach that involves deviating from the approved plans without proper authorization or documentation is professionally unacceptable. This failure violates the fundamental principle of accountability in electrical installations, especially for fire alarm systems. Specifically, it breaches the requirement to follow approved plans and specifications, which are established based on code requirements and system design for optimal performance. Such deviations can lead to system malfunctions, false alarms, or failure to activate during a fire, directly compromising life safety and potentially leading to legal liability for the electrician and the building owner. Another incorrect approach, which is to proceed with the installation as initially planned despite the observed discrepancy, is also professionally unacceptable. This demonstrates a lack of due diligence and a failure to identify and rectify potential issues before they become embedded in the system. It ignores the potential for the discrepancy to impact system performance or code compliance, thereby failing to uphold the electrician's duty to ensure a safe and compliant installation. This can result in the system not meeting its intended protective function, leading to significant safety risks and potential legal repercussions. A further incorrect approach, which is to install the system according to the contractor's verbal instructions that contradict the approved plans, is a severe ethical and regulatory failure. Verbal instructions, especially when they deviate from documented and approved specifications for a life safety system, are inherently unreliable and lack the necessary authority and traceability. This bypasses the established process for design changes and approvals, which is crucial for maintaining system integrity and ensuring that all stakeholders are aware of and agree to any modifications. This action directly undermines the integrity of the installation and exposes the electrician to significant liability. The professional reasoning process for similar situations should involve a clear understanding of the hierarchy of authority and documentation. Approved plans and specifications take precedence. Any observed discrepancies or proposed changes must be addressed through formal channels, which typically involve communication with the design engineer, architect, or relevant authority having jurisdiction. The electrician's role is to execute the approved design safely and competently. If a deviation is necessary or a conflict arises, the professional must pause the work, document the issue, and seek clarification and written approval before proceeding. This systematic approach ensures that all installations are compliant, safe, and auditable. Question 15. The investigation demonstrates that a recently delivered panel board intended for a critical facility has bus bars that appear to be of a smaller physical dimension than typically specified for its rated amperage, and the manufacturer's documentation for this specific model is either missing or unclear regarding the precise bus bar ampacity. The client is pressuring for a swift installation to avoid project delays and associated costs. As the master electrician overseeing the installation, what is the most ethically and regulatorily sound course of action? Option A. Install the panel board as is, assuming the manufacturer would not ship a non-compliant product, and rely on the existing overcurrent protection devices to adequately protect the circuits. Option B. Refuse to install the panel board until the manufacturer can provide definitive documentation confirming the busbar ampacity, or until a qualified electrical engineer can verify its compliance with the National Electrical Code, NEC, for the intended overcurrent protection and load. Option C. Install the panel board, but immediately label it with a significantly reduced amperage rating, lower than what the overcurrent protection devices are set for, to err on the side of caution. Option D. Proceed with the installation, and if any issues arise during testing or operation, address them at that time, as the primary goal is to meet the project deadline. The correct answer is B. Refuse to install the panel board until the manufacturer can provide definitive documentation confirming the busbar ampacity, or until a qualified electrical engineer can verify its compliance with the National Electrical Code, NEC, for the intended overcurrent protection and load. Explanation. This scenario presents a professional challenge because it involves a conflict between immediate cost-saving pressures and long-term safety and code compliance. The master electrician is tasked with ensuring the integrity of critical electrical infrastructure, which directly impacts the safety of occupants and the reliability of the facility. The temptation to overlook minor deviations for expediency is a common ethical pitfall in the trades. The correct approach represents best professional practice because it prioritizes adherence to the National Electrical Code, NEC, and the manufacturer's specifications. The NEC, as adopted by the relevant jurisdiction, is the minimum standard for safe electrical installations. Deviating from busbar sizing calculations or overcurrent protection requirements, even if seemingly minor, can lead to overheating, insulation failure, fire hazards, and potential equipment damage. Upholding these standards is not just a regulatory requirement, but an ethical obligation to protect life and property. An incorrect approach that involves accepting the panel board with undersized busbars, despite the manufacturer's stated capacity, represents a significant regulatory and ethical failure. This directly violates NEC requirements for conductor and busbar sizing, which are designed to prevent excessive temperature rise. It also breaches the ethical duty to install equipment according to its listed and labeled purpose and capacity. Furthermore, failing to document or report such a deviation is a concealment of a potential hazard. Another incorrect approach, which is to install the panel board as is and simply label it with a lower amperage rating than its busbar capacity would normally allow, is also professionally unacceptable. While this might seem like a compromise, it still bypasses the proper design and engineering process. The NEC requires that overcurrent devices be selected to protect conductors and equipment based on their ampacity. Simply derating the perceived capacity without proper engineering justification or adherence to code-specified methods for busbar sizing and overcurrent protection is a form of circumventing safety standards. It creates a false sense of security and does not address the underlying issue of the busbars not meeting the intended design parameters for the intended circuit protection. A third incorrect approach, which is to proceed with the installation and assume the existing overcurrent protection is adequate without verifying busbar capacity, is a failure of due diligence. A master electrician has a responsibility to ensure all components of an electrical system are properly sized and protected. Relying on assumptions rather than verifying critical parameters like busbar ampacity against the installed overcurrent protection and the overall system design is a dereliction of professional duty and a violation of the NEC's intent for safe and reliable installations. The professional reasoning process for similar situations should involve a systematic approach. 1. Identify the core issue. Is there a discrepancy between the installed components and the code requirements or manufacturer specifications? 2. Consult the relevant codes and standards, in this case the NEC, specifically articles pertaining to panel boards, switchboards, busbars, and overcurrent protection. 3. Review manufacturer documentation. Ensure the equipment is installed and operated within its listed parameters. 4. Assess the risk. Understand the potential consequences of any deviation from standards. 5. Communicate and document. Clearly communicate findings to the client or responsible party and meticulously document all observations, decisions, and actions taken. 6. Seek expert advice if necessary. If there is ambiguity or a complex situation, consult with a qualified electrical engineer or the authority having jurisdiction, OJ. 7. Prioritize safety and compliance. Never compromise on safety or code requirements for expediency or cost savings. Question 16. Upon reviewing the specifications for a new industrial motor installation, the master electrician needs to select the appropriate overcurrent protection device. The motor nameplate indicates a full load amperage flaw and a service factor. The motor is located in an area where dust accumulation is a concern, and the manufacturer's documentation specifies a particular type of listed motor controller. Considering the principles of risk assessment and electrical safety, which of the following approaches best ensures the protection of the motor and the electrical system? Option A. Choose a standard molded case circuit breaker with a trip rating at or below the motor's FLA, without specific consideration for the dusty environment or the motor controller's listing. Option B. Select an overcurrent device based on its physical size and the availability of similar devices in stock, assuming it will provide adequate protection for the motor. Option C. Select a circuit breaker with an inverse time delay characteristic, whose trip setting is based on the motor's FLA and service factor, ensuring the breaker is listed for use in dusty environments and compatible with the specified motor controller. Option D. Install a fuse with a time delay characteristic that is sized to be at least 125% of the motor's FLA, irrespective of the environment or the motor controller's specifications. The correct answer is C. Select a circuit breaker with an inverse time delay characteristic whose trip setting is based on the motor's FLA and service factor, ensuring the breaker is listed for use in dusty environments and compatible with the specified motor controller. Explanation. This scenario presents a professional challenge because the master electrician is tasked with ensuring the safety and reliability of an electrical system by selecting appropriate overcurrent protection. The challenge lies in understanding the nuances of different overcurrent protection devices, their application in specific environments, and the potential consequences of improper selection, which can range from nuisance tripping to catastrophic equipment failure or fire. The risk assessment approach is crucial here, as it involves proactively identifying potential hazards and implementing measures to mitigate them. The correct approach represents best professional practice because it prioritizes a thorough understanding of the equipment's operational characteristics and the applicable electrical code requirements. Specifically, selecting an overcurrent device that is listed for the specific application and has a trip rating that is not in excess of the equipment's ampacity, while also considering the potential for short-circuit current, directly aligns with the fundamental principles of electrical safety and code compliance. This proactive and informed decision-making process minimizes the risk of electrical hazards and ensures the longevity of the installation. An incorrect approach that involves selecting a standard fuse or circuit breaker without verifying its suitability for the specific motor application or its listed interrupting rating is a significant regulatory and ethical failure. This bypasses the critical step of ensuring the device can safely interrupt the maximum fault current that could occur, potentially leading to device failure, fire, or severe damage to the motor and connected equipment. Another incorrect approach, such as choosing a device solely based on its physical size or ease of installation, ignores the fundamental safety requirements of overcurrent protection and violates the electrician's duty to protect persons and property. Relying on past practices without verifying current code requirements or equipment specifications is also a failure, as electrical codes and equipment designs evolve. The professional reasoning process for similar situations should involve a systematic risk assessment. This begins with identifying the equipment to be protected and its operational parameters. Next, the master electrician must consult the relevant sections of the applicable electrical code, e.g., National Electrical Code in the U.S., to determine the specific requirements for overcurrent protection for that type of equipment. This includes understanding the rules for sizing, type of device, and interrupting capacity. Finally, the electrician must verify that the selected device is listed and labeled by a recognized testing laboratory for the intended application, and that its specifications meet or exceed the code requirements and the equipment's needs. This methodical approach ensures safety, compliance, and professional integrity. Question 17. The audit findings indicate a recurring issue with power factor correction in several industrial facilities. When discussing the underlying causes, the maintenance team presented several explanations for the observed inefficiencies. Which of the following explanations best reflects a correct understanding of how inductive and capacitive elements influence AC circuit performance, as required for a master electrician's competency? Option A. The primary factor affecting power factor in AC circuits is the total resistance, and reactive components have a negligible impact on overall efficiency. Option B. Inductive and capacitive reactances are additive and directly increase the total impedance of an AC circuit, regardless of their individual characteristics. Option C. Inductors and capacitors behave identically in AC circuits, both increasing opposition to current flow as frequency rises. Option D. Inductive reactance, which opposes changes in current, increases with increasing frequency, while capacitive reactance, which opposes changes in voltage, decreases with increasing frequency. The correct answer is D. Inductive reactance, which opposes changes in current, increases with increasing frequency, while capacitive reactance, which opposes changes in voltage, decreases with increasing frequency. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires a master electrician to interpret and apply knowledge of AC circuit behavior, specifically concerning capacitance and inductance, in a practical, non-calculation-based context. The challenge lies in discerning the fundamental operational principles and their implications for system performance and safety, rather than simply solving for numerical values. The audit findings suggest a potential misunderstanding or misapplication of these principles, which could lead to inefficient installations, equipment damage, or safety hazards. Accurate judgment is crucial to ensure compliance with electrical codes and best practices for system design and maintenance. Correct approach analysis. The correct approach demonstrates a deep understanding of how inductive and capacitive elements affect AC circuits. It recognizes that in an AC circuit, an inductor opposes changes in current, leading to inductive reactance, and a capacitor opposes changes in voltage, leading to capacitive reactance. When both are present, their reactances combine with resistance to form impedance, which dictates the overall opposition to current flow and the phase relationship between voltage and current. Understanding that inductive reactance increases with frequency, while capacitive reactance decreases with frequency, is fundamental to predicting system behavior under varying conditions. This knowledge is essential for troubleshooting, system design, and ensuring that electrical equipment operates within its intended parameters, aligning with the principles of safe and efficient electrical installations as mandated by the relevant electrical code. Incorrect approaches analysis. One incorrect approach might focus solely on the resistive components of a circuit, ignoring the significant impact of inductive and capacitive reactances on AC behavior. This failure is a direct violation of the principles of AC circuit analysis and would lead to an incomplete and inaccurate understanding of system performance. It ignores a critical aspect of electrical engineering that is directly addressed by electrical codes concerning power factor correction and harmonic distortion, which are heavily influenced by reactive components. Another incorrect approach might incorrectly assume that inductive and capacitive reactances are additive in a simple arithmetic manner, without considering their opposing phase relationships. This misunderstanding would lead to erroneous conclusions about the total impedance and current flow in the circuit. Ethically and regulatorily, this demonstrates a lack of fundamental knowledge required for a master electrician, potentially resulting in unsafe system designs or troubleshooting errors. A third incorrect approach might confuse the behavior of capacitors and inductors, attributing the characteristics of one to the other. For instance, suggesting that an inductor's reactance increases as frequency decreases, or that a capacitor's reactance is independent of frequency. Such a fundamental error in understanding the behavior of these components would render any subsequent analysis or decision-making unreliable and potentially hazardous, failing to meet the competency standards for a licensed master electrician. Professional reasoning. When faced with audit findings related to AC circuit behavior, a master electrician should first review the specific components and their expected roles within the system. The professional reasoning process involves 1. Identifying the presence and function of inductive and capacitive elements. 2. Recalling the fundamental principles of inductive and capacitive reactance and their dependence on frequency. 3. Understanding how these reactances, along with resistance, contribute to the circuit's impedance and affect current and voltage phase relationships. 4. Considering the implications of these behaviors on system efficiency, power factor, and potential for resonance or harmonic issues. 5. Consulting relevant sections of the electrical code that address AC circuit design, power factor, and harmonic mitigation to ensure compliance and best practices. This systematic approach ensures that decisions are based on sound electrical theory and regulatory requirements, leading to safe and effective electrical installations. Question 18. Examination of the data shows an industrial facility is installing new electrical distribution in an area identified as having a moderately corrosive atmosphere due to chemical processing. The master electrician is tasked with selecting the appropriate wiring method and materials for conduit runs that will be exposed to these conditions. Which of the following approaches best adheres to the National Electrical Code, NEC, requirements for ensuring the integrity and safety of the electrical installation? Option A. Select PVC conduit rated for corrosive environments, ensuring all fittings and supports are also compatible and suitable for direct burial or exposed use as required by the installation location. Option B. Install non-metallic sheathed cable, NMB, in exposed locations, relying on its inherent insulation to protect the conductors from the environment. Option C. Utilize standard galvanized steel rigid metal conduit, RMC, with a standard factory coating, as it offers good physical protection and is commonly used in industrial settings. Option D. Employ flexible metal conduit, FMC, with standard insulation, as it is easy to install and can accommodate minor movements in the facility. The correct answer is C. Utilize standard galvanized steel rigid metal conduit, RMC, with a standard factory coating, as it offers good physical protection and is commonly used in industrial settings. Explanation. This scenario presents a common challenge for master electricians, selecting the appropriate wiring method and materials for a specific environment while ensuring compliance with the National Electrical Code, NEC. The professional challenge lies in balancing cost-effectiveness, long-term reliability, and adherence to safety standards, particularly when dealing with potentially corrosive atmospheres. A master electrician must possess a thorough understanding of NEC requirements for various wiring methods and material specifications to make informed decisions that protect both personnel and property. The correct approach involves a detailed review of the NEC articles pertaining to wiring methods and materials in corrosive environments. Specifically, Article 300, Wiring Methods and Materials, and relevant sections within articles covering conduit, cable, and enclosures are critical. The NEC mandates specific types of raceways and enclosures that can withstand corrosive agents to prevent premature degradation, insulation failure, and potential fire hazards. choosing materials specifically listed and identified for use in such environments, such as certain types of PVC conduit or corrosion-resistant metallic conduit with appropriate coatings, and ensuring proper installation techniques to maintain the integrity of the system, represents best professional practice. This ensures the electrical system's longevity and safety, fulfilling the master electrician's ethical and legal responsibility. An incorrect approach would be to select standard materials without considering the corrosive nature of the environment. For instance, using standard galvanized steel conduit without a suitable coating, or employing non-rated cable types in a location exposed to chemicals or high humidity would be a direct violation of NEC requirements. This failure stems from a lack of due diligence in assessing environmental conditions and their impact on material selection. Ethically, this demonstrates negligence and a disregard for the safety of the installation. Another incorrect approach might be to prioritize cost over safety by selecting a cheaper, less durable material that is not rated for the specific corrosive conditions, leading to potential system failure and safety risks. This violates the professional obligation to provide a safe and reliable electrical installation. Professional decision-making in such situations requires a systematic process. 1. Identify the environmental conditions and potential hazards, e.g., presence of specific chemicals, moisture levels, temperature extremes. 2. Consult the NEC, focusing on Article 300 and any specific articles related to the proposed wiring method. 3. Determine the appropriate wiring methods and materials permitted by the NEC for the identified conditions. 4. Verify that the selected materials are listed and labeled for the intended application and environment. 5. Consider the long-term performance and maintenance requirements of the chosen system. 6. Document the decision-making process and the rationale for material selection. Question 19. Performance analysis shows that a new commercial building project requires legally required standby systems to ensure continued operation of essential services and occupant safety during power outages. The design includes a generator intended to power critical equipment and provide emergency lighting. As the master electrician overseeing the installation, what is the most critical step to ensure full compliance with the National Electrical Code, NEC, regarding the integration of the standby power source and emergency lighting? Option A. Confirm that the standby generator is capable of powering all building loads, including emergency lighting, and that the transfer switch is designed to isolate the generator from the normal power supply. Option B. Verify that the selected standby generator's capacity and transfer switch are rated to support the essential loads, and that the emergency lighting circuits are exclusively supplied from the emergency power source as defined by the NEC. Option C. Install the standby generator and connect the emergency lighting to the generator's output, assuming that any generator powering essential equipment will automatically meet emergency lighting requirements. Option D. Ensure the standby generator meets the manufacturer's advertised specifications for continuous operation, and that the emergency lighting is connected to the same circuit as the general building power. The correct answer is B. Verify that the selected standby generator's capacity and transfer switch are rated to support the essential loads, and that the emergency lighting circuits are exclusively supplied from the emergency power source as defined by the NEC. Explanation. Scenario analysis. This scenario presents a common challenge for master electricians, ensuring compliance with emergency system requirements in a complex building project. The challenge lies in interpreting and applying the National Electrical Code, NEC, requirements for legally required standby systems, specifically concerning the integration of emergency lighting and standby power sources. A master electrician must not only understand the technical aspects of these systems, but also their critical role in life safety and the legal ramifications of noncompliance. The pressure to complete the project on time and within budget can create a temptation to overlook or misinterpret nuanced code requirements, making meticulous attention to detail and a thorough understanding of the NEC paramount. Correct approach analysis. The correct approach involves a comprehensive review of the NEC, specifically Article 700 Emergency Systems and Article 701 Legally Required Standby Systems. Determine the precise requirements for the building's occupancy and use. This includes verifying that the selected standby power source, generator, meets the capacity and transfer switch requirements outlined in the NEC for legally required standby systems. Furthermore, It necessitates confirming that the emergency lighting circuits are supplied from the emergency power source as mandated by the code, ensuring they will function independently of the normal power supply during an outage. This approach represents best professional practice because it directly addresses the life safety implications of emergency and standby systems, adhering strictly to the established safety standards and legal obligations defined by the NEC. Ethical practice demands prioritizing public safety above all else, and this approach ensures that the installed systems will perform as intended during an emergency, protecting occupants. Incorrect approaches analysis. One incorrect approach involves assuming that any standby generator is sufficient for legally required standby systems without verifying its specific compliance with NEC Article 701. This is a regulatory failure because Article 701 details specific performance and installation requirements for these systems, including load calculations, transfer switch types, and duration of power, which may not be met by a generic standby generator. Ethically, this approach risks the safety of building occupants by potentially installing an inadequate system. Another incorrect approach is to connect emergency lighting circuits directly to the normal power supply, with the understanding that the standby generator will power the entire building, including emergency lights, during an outage. This is a critical regulatory failure, as NEC Article 700 mandates that emergency lighting circuits be supplied from the emergency power source, which is distinct from legally required standby systems, to ensure immediate and reliable illumination independent of the normal power source and the transfer time associated with standby systems. Ethically, this creates a significant life safety hazard, as emergency lighting may not activate promptly or reliably during an emergency. A third incorrect approach is to rely solely on the generator manufacturer's specifications without cross-referencing them with NEC requirements for legally required standby systems. While manufacturer specifications are important, they do not supersede the legal mandates of the NEC. This is a regulatory failure because the NEC dictates specific performance criteria and installation methods that must be met, regardless of what a manufacturer might claim for a general-purpose generator. Ethically, this can lead to a system that is technically functional but legally non-compliant and potentially unsafe in a real emergency. Professional reasoning. Professionals should employ a systematic decision-making framework that begins with a thorough understanding of the project's intended use and occupancy classification. This dictates the applicable NEC articles and their specific requirements. The next step is to consult the relevant NEC articles, Article 700 and 701 in this case, and any local amendments. A critical part of this process is to verify that all components, including the power source and transfer equipment, meet the code's stringent requirements for emergency and legally required standby systems. Documentation is key. Maintaining records of code interpretations, design choices, and installation verification provides a defense against potential future issues and demonstrates due diligence. When in doubt, consulting with the authority having jurisdiction or a qualified electrical engineer is a crucial step to ensure correct interpretation and application of the code, thereby upholding professional responsibility and public safety. Question 20. The risk matrix shows a moderate likelihood of increased operational costs and a high impact on occupant comfort due to inadequate illumination levels in a newly renovated office space. The client has requested a lighting solution that is both cost-effective in the short term and compliant with current energy efficiency standards. Considering these factors, which approach to lighting fixture and control system selection best mitigates these risks and ensures professional compliance? Option A. Opt for standard fluorescent lighting fixtures, as they are a proven technology, and implement a simple manual on/off switch system to control illumination. Option B. Install the most aesthetically pleasing lighting fixtures available within the client's initial budget, assuming that modern fixtures inherently offer sufficient energy efficiency. Option C. Select lighting fixtures based on their historical performance in similar projects, without specifically verifying their current energy consumption ratings or the availability of advanced control integration. Option D. Prioritize the selection of LED lighting fixtures with integrated occupancy sensors and daylight harvesting capabilities, ensuring the chosen fixtures meet or exceed the efficacy requirements outlined in the local energy code. The correct answer is D. Prioritize the selection of LED lighting fixtures with integrated occupancy sensors and daylight harvesting capabilities, ensuring the chosen fixtures meet or exceed the efficacy requirements outlined in the local energy code. Explanation. Scenario analysis. This scenario presents a common challenge for master electricians, balancing the immediate need for functional lighting with long-term energy efficiency and compliance with evolving standards. The challenge lies in selecting appropriate lighting fixtures and control systems that not only meet the client's immediate operational requirements, but also adhere to current energy codes and best practices for sustainability and occupant comfort. A failure to adequately assess these factors can lead to increased operational costs, premature obsolescence of the installation, and potential non-compliance with local electrical codes and energy efficiency mandates. Correct approach analysis. The correct approach involves a comprehensive assessment of the space's intended use, occupant needs, and relevant energy efficiency standards. This includes evaluating the efficacy of different lighting fixture types, e.g., LED vs. older technologies, and their suitability for the specific environment. Crucially, it necessitates the integration of appropriate lighting control systems, such as occupancy sensors and daylight harvesting controls, to minimize energy consumption when full illumination is not required. This approach aligns with the principles of responsible electrical design, prioritizing energy conservation, occupant well-being, and adherence to the National Electrical Code, NEC, and any applicable local energy codes, which increasingly mandate energy-efficient lighting solutions. Incorrect approach is analysis. Selecting the most aesthetically pleasing or lowest initial cost fixture without considering energy performance or control integration represents a failure to adhere to modern electrical code requirements and best practices for energy efficiency. This approach ignores the long-term operational costs and environmental impact, potentially leading to a system that is inefficient and costly to operate. Installing a system that solely relies on manual switching, even with energy-efficient fixtures, overlooks the significant energy savings achievable through automated controls. This fails to meet the spirit, and often the letter, of energy codes that encourage or mandate the use of advanced lighting controls to reduce energy waste. Choosing fixtures based on outdated specifications, or without verifying their compliance with current lumen output and energy consumption standards, is a direct violation of code requirements and professional responsibility. This can result in an installation that is not only inefficient, but also potentially fails to provide adequate illumination levels, impacting safety and productivity. Professional reasoning. Master electricians must adopt a holistic approach to lighting design and installation. This involves 1. Understanding the client's needs and the functional requirements of the space. 2. Researching and selecting lighting fixtures that offer optimal performance, energy efficiency, and longevity, referencing manufacturer specifications and relevant standards. 3. Integrating appropriate lighting control systems that enhance energy savings and occupant comfort, ensuring compliance with NEC Article 410 fixtures and any specific energy efficiency mandates in the jurisdiction. 4. Consulting local building and energy codes to ensure all aspects of the lighting design meet or exceed regulatory requirements. 5. Considering the total cost of ownership, including initial installation, energy consumption, and maintenance, rather than focusing solely on upfront costs.